Okay, so the next topic we're going to talk about is the Triac. Now remember that the Diact is, the Triac is exactly like the Diact, except it has a gate. Okay, so the Diact, as you should know by the slide presentation, it basically needs a forward voltage in order to short, or it also can use a reverse voltage. Okay, so it needs a certain amount of potential forward to break over and short, or it needs a certain amount of reverse potential to break over and short. Okay, or become a shorted switch, or saturate, whichever term you want to use. Okay, now the Triac was a little different in the sense that it can operate with a gate. Okay, so it's the same concept. So if there's no gate potential and there's nothing on the gate and the gate is left just hanging, this device would act exactly like a Diact. Okay, for all intents and purposes. Now let's go through the quadrants, and then I'll go into the phase control circuit that we saw with the silicone control rectifier. So in quadrant 1, now notice that we have top portion and bottom portion. We have M2 positive on the top, M2 negative on the bottom. I'm not too concerned about M1 because whatever M2 is, M1 is the opposite. Okay? So as far as what's going on relationship-wise, notice that anything above the line here is forward voltage activated. In other words, current flows from this being the anode, the cathode, right, down to up, from MT1 to MT2. Anything below the line here, we're in quadrant 3 and 4. Now notice the only difference between quadrant 1 and 2 is in fact the polarity of the gate, okay, which suggests that if this is our potential, this can be activated by the forward voltage going to the breakover voltage, or positive or negative gate potential. Either or will activate this guy in short amount. Okay, the next part of this is this one operates in reverse voltage. Okay, so this one is operating in the reverse current field because you can see that M2 is negative, right? And current is flowing in the opposite direction. And again, the same concept, right? Is that the gate can be positive or negative, and the reverse potential, two things can activate this guy to a short. It'd be reverse potential, right? We have enough reverse potential that it goes over to the breakover voltage, or the gate could be positive or negative to a certain trigger point. Okay, now taking that concept, now let's look at our next slide. Here's our Triac phase controller. Okay, now here's our Triac. Okay, we have the device, right? This is the device that'll be controlling it, or will be initiating the output. The output's taken at this point. Okay, we have 2 diodes. Notice the diodes are facing the opposite ways, right? In other words, for anything to get through, we need this guy to be positive, negative, and this guy to be positive, negative. Okay, we've got a resistor that we can adjust. And then we have these 2 circuits, okay? These are just basically snubber circuits. And like I described earlier, they're just to protect from spikes and any other little transient conditions. Because what happens, and notice that they're around the Diact, which is here. There happens to be a Diact. And it's around the Triac, okay? And the idea is that these devices, if there's ever a spike in the line somewhere, these devices could be triggered, okay? So we don't want that, so we put a snubber circuit on either side of that. Okay. So if we go through the scenarios now, if we have a positive potential and a negative potential here, D2 is off, okay? D1 is on. D1 puts a positive potential here at VA, okay? And VA, and then we adjust R1 to be at a certain value, okay? Now, what we have here is we set up the Diac to trigger, right? So the Diac is our trigger. So remember, the Diac operates and needs a certain forward potential or reverse potential. It can be either, okay? But in this case, it's going to be forward, and I'll explain why, because this point will always be positive. So right now, he needs to see a certain potential. We can adjust based on the size of the sine wave, that potential with R1, so he'll drop a certain potential, and then the remainder will be left here. And whatever he sees potential-wise, then if he sees enough potential, in other words, enough of the sine wave gets produced or adjusted, then he triggers and activates him and shorts, and the load sees whatever, when he shorts, he sees whatever the sine wave is left. And this is where we get this kind of sine wave output here. Notice it's very similar to what we saw with the phase controller on the silicone control rectifier, okay? Now, when things change, and this goes negative and positive, now this is where this differs. Notice that the silicone control rectifier can only really do positive alternation. It couldn't do negative, okay? Now, this guy can do negative because, and I'll go through it. So he goes positive now, he turns off, he turns on, this point's still positive. We still can adjust this guy to set the trigger point, right? This guy sees enough, say again, it's the same scenario as was before. There's a positive potential here. He has to see a certain amount to trigger him. But what this guy sees, now we're triggering him, but don't forget, he sees a negative potential, okay? So now remember, going to our phase, right? We've just made, now this is M2 on the top, M1 on the bottom. We've just made him negative with a positive potential. This is going to provide us with a shift in current. So in our first scenario, it was this, right? Current moving this way. In this scenario, current's moving this way. This is why we get the negative alternation. It's got nothing to do with the actual sine wave coming this way. It's got everything to do with the triggering of the triac and the conditions in which, what quadrant we fall under, okay? And again, we can adjust this trigger point based on whatever our one's setting is. And that's how the Triac phase controller works.